Okay. Hi. I thought I'd give a short, um, lecture on on how you can use folds to define various kinds of functions. So I'm going to go down here in the. I'm going to run GHCI and look. Remember the type of fold L and the type of fold R. And you'll notice that in this function, so they're both, the final result is that this T you can take as a list of things of type A. We'll talk maybe about foldable a little bit later. That's a type class that basically says fold can work on this thing. And folds happen to work, lists are foldable. So this could be list A in a more specialized form. Let me pull it up here so we can look at this. Copy. Well, let me grab them both. And so we can get rid of that foldable thing, the foldable business, by making this a list, which is what we're thinking about right now. So there is, so functions that you write using folds can apply to more types than just lists if you specify them to be foldable. But here's the key thing is that the arguments come in a different order here. In fold L, you get the answer and then you get the next input from the list. In fold R, you get the next input off the list you're operating on, and then you get the answer and you return the answer. So like we did, I think in the lecture notes, I said something like, let me go down here. I said something like, okay, fold L, flip colon 1 through 10. I got to give it the base case. So if I look at the type up here, it'd say, what's the answer if the list is empty? And so there we go, the empty list. And this was the same as, this reverses the list. Now, what happens if I do fold R? Now, if I try the same trick, well, maybe I should show you the type. What's the type? So the type of colon is this. And what's the type of flip colon is, it wants, in colon, cons wants an element of the list first and then the list. That's, you're going to glue it on. Flip cons wants the list first and then the element of the list to cons on. And so that's why this works running through here, is because the arguments on fold L are flipped. So if I just tried to do a fold R with the same thing, it's not going to work. It's going to have a type error. And the type error is that, oh no, it doesn't know what to do. There's a problem with the type in the first argument of fold R, flip cons. Now, what if I just do this? I just say, okay, look, okay, put cons back in the right order. Well, that just puts a cons between every pair of elements in the list and then conses them all together. So fold R cons gives back the same list. Fold L of flip cons reverses the list. So the fold L oftentimes ends up building things in the reverse order from what you really might want. And fold R retains the order of the original list, usually when you're building things using that. So, especially when you're building a list, for certain things it doesn't matter. Like if we're doing plus, which is associative, then it doesn't matter. Plus works, A plus B, 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. And you might remember that fold L is grouping it to the left. So this would kind of be the fold L pattern. And fold R is grouping things to the right. So if I do a fold L of plus, plus with 0 on 1, 2, 3, that's going to give me the pattern on the left there, which the answer is 6. And a fold R is going to give me. All right, so those are folds. But let's see, how do we write this function in here? Like here, we're just using a section or a flip, flip cons is what we've used. So there's a nice function, quite often useful function called split at. Okay, so split at has this type. Copy. I'm going to put it up here. Paste, and I'm going to write my own version. I split at that has the same type. So what does split at do? You might guess is, if you say split at 5, 1 through 10, you get back the list that was split. Where the left, you get back a pair of lists where the first list is the one that has the first 5 elements and the second one has everything after that. So like if I do, 20, first one has the first 5 elements and the second one has that. So can we write this with a fold? And I split at, and so it's got to have an int. So let's call it J, and it's got to have a list, which we'll call X's. And remember, or maybe I didn't say this before, you haven't read it, is that, when I'm defining my split at in this way, I'm not using recursion. I'm using fold L or fold R. Now, for some applications, it doesn't matter. Like if the order of the elements in the list doesn't matter to you, then, you oftentimes can get away with using a fold L, which might be slightly more efficient, but the answer is going to look funny to you. And in some cases, you actually care. So since we want to try and, since these elements occur in the same order as the elements in the original list, let's use fold R. And so what is this first argument to fold R? It's this function here. So you know what? I'm just going to punt. I'm going to say, okay, look, I'm not going to worry about what that function f is right now. And what is the default return value of this thing? Well, the return value has to be a pair of lists. And so if my input is the empty list, then the pair of empty lists is the right thing. So like if I say split at, 1 empty, it comes back with a pair of the empty lists. So I know that. And then I've got x's. Now, in a functional style, we might just get rid of that last argument and say, look, my split at J is equal to fold L F empty empty. And where F, and now I'm going to define F. So I have to figure out, I have to look, okay, I'm on fold R, and here's the type of the function that I need to write down here. Here's what F has to be. And so we look at the input from, if this list is the thing that we're folding over. And so the first input is something that's just straight up from the list. And the second input is something that's an answer. Now, I could write just here answer and give you a definition, except that in this case, the answer itself is going to be something, a pair of lists. So I might as well give them names using pattern matching. So answer 1 list and answer 2. And now, what do I do? Oh, I'm in trouble because I need to be able to count how far I am through the list. And so I can't really do that like this. So here's a trick that I'm going to do is I'm going to say, okay, I'm going to provide you with the list X's. And then over here, the input is going to actually be, I'm going to zip together the 2 lists, the infinite list of 1 going on forever with X's. And so I should show you down here, like, okay, zip of the infinite list with, let's say, X, Y, Z, Z, Y, will give back a list where 1 is paired with X, 2 is paired with the second character Y, 3 is paired with the third character Z, 4 and 5, and so on. So this will give me back actually not just the X, it will give me back something like a K comma X pair. And so now I have enough information. I can say, okay, look, if K is less than or equal to J, which is where I want to split, then I put X onto A1 and I don't do anything to A2. Else, I leave A1 alone and I put I glue X onto A2. So there's a function for my split at. So let's just see if it works. Let's go down here and try. I got to load. What is it? Using folds. Okay, it loaded. And so my split at, what was the last one that we did was split at 1. Okay. 1. Okay. What about 0? Okay, I could split at 0. What if I split at, 5? What if I split at 11? Okay, it puts everything over. Okay, so this is a good implementation. This is an implementation of my split at using a fold R. Now, what if we had changed this to a fold L? And now, if I do that, I have to swap these arguments because in the type of fold L versus the type of fold R, fold L, it wants the answer first and then the X, the input X's. And otherwise, I think everything else stays the same. So I can try and see, I can see what happens with this. And so I need to reload it. And if I do this one, the lists are in the reverse order. So the fold L is not doing entirely the right thing. But suppose that you were thinking of these lists as sets. It didn't really matter what the order of the elements was. It only mattered that the elements were the same, split at 5 dot dot 10. These two lists have the same element. This list and this list have the same element, and this list and this list have the same element. So, but it means we're probably better off with doing it with a fold R. Now, there's one other bit here that's maybe a little bit less readable than it can be, is that you can say, okay, if k is less than or equal to j, it's equal to this, and otherwise, it's equal to that. So this could be, it's almost a matter of personal taste. Remember, otherwise is just true. But this one avoids completely using an if, and it maybe lays out the cases more clearly. If excuse me, if there were 3 cases, you would definitely, rather than having nested ifs, you'd want to do it this way. So, okay. There's my split at written using a fold. And I think sometimes it's easier to just kind of just put an F in there and say, look, I'll define that later once I start thinking about it. And then when you start thinking about it, you may run into a constraint like this. Uh-oh, I need to have the index in there. Okay, what about unzip? So if I had zip of, I showed you this before. Oh, is that a caps lock? No, I accidentally pressed a shift. Okay. If I had that list, could I put it back into what unzip does? Now, I should tell you that it is the last thing that was evaluated. Now, if I do that and then I type it, oh, it's still the last thing. Good. Okay. So it is the last thing that was actually evaluated. So I can say like unzip to see what it actually does and just apply it to it. And it says, oh, okay. And it puts them back together in their separate lists. Now, if I wanted to apply zip to that, I could uncurry zip, apply that to it, and then I get back this thing. Why did I have to uncurry it? Because the type of zip, it wants its arguments at one at a time, but what's the type of uncurry zip? Oh, it takes a pair of lists just like this one. Okay. So what we want to do is we're going to do unzip. What's the type of unzip? Okay, unzip has this type, and so I'm going to go up here and I'm going to make a my unzip so that I don't clobber that one. And so my unzip simply takes a list of pairs. So I'm going to say X, Y's just to kind of indicate maybe sort of that they're X, Y pairs. And again, if I want to save the ordering, you'll notice that these things don't get like flipped around in the reverse order. So I'll just say F. And what is the answer if the list is empty? Well, then it's a pair of empty lists. Now I can apply this to X, Y's. But actually, I may not need them, so I'm just going to get rid of them since it's the common last argument here. And so now let's start to define F. Okay, so F. Now what's F going to take? It's a fold R. So F is first going to take an input, which is a pair. So this is the input from the list that I'm operating has this type. So the first one is going to be an X comma Y. And the answer that I'm operating on is something of this type. So I can call it like X's and Y's. Now, how can I build the right thing? Well, I want to put the X on the X's and the Y on the Y's. Oh, I better make the names the same. Okay, so that works. Okay, let's look at okay, that worked. And so now I can try my unzip on oh, let's say zip maybe I better show you what the zip is first. Now, of course, the natural thing to do here is, is to include quick check. And to check these things, and then just go down here and make a property, and the property should be that and so this is going to take an int, and it's going to take a list, and the claim is going to be that, split at jx is identically equal to my split at of jx's. And then we can write a property down here that says, unzip my unzip. This just takes an x's definition is that unzip x's is equals to my unzip x's. Okay. And save that. I can come down here and try loading it again. And it loaded. Good, that's good. So now I can say quick check. Prop split at my split at, well, lowercase. And I need to give it an integer. And so that thing is, if you look at the type up there, it's expecting an int. And then I'll just make the list a list of, so it's a int arrow, let's say list of int arrow bool. So I'm basically saying, look, don't worry about it being any arbitrary type. Make it integers. And oh, I forgot to save this. How do I get back to my terminal? I accidentally closed it. Okay. Okay. And it doesn't remember what I was doing, and so I was doing a quick check on prop split. You know, it might even be easier to put the type up here that I want. And the type that I want there is that it's an int arrow of int arrow bool. Change this to character now, and it'll test with a randomly generated bunch of characters. And so there's that. Now, I guess what I'm saying is that I could make this a little bit easier to do by just making this what I wanted up here and say, look, here's what I'm interested in testing on is ints. And load it, and then get rid of all this typing business down here because I've put the right type up there and it passed 100 tests. What about this one? Again, same thing. We can make this like, you know, some arbitrary thing, but, you know, we could make it int and characters. All right. And if I save that and I load it down here, I can say quick check prop unzip my unzip. That's 100 tests. So I don't know if that extra bit was worth it, but you know, it might be to kind of like give yourself more evidence. It's not a proof that the two are identical. And if we wanted to do a proof, we'd have to do it by recursion, by induction on the structure of the list. And we hopefully will get to that soon. All right. So that's that. Let's see, I can stop.